Hello, I'm Doug Montgomery. I'm your instructor in the Design of Experiments MOOC, and I would like to welcome you to our February Fireside chat that accompanies the MOOC. And for those of you that are new to this whole experience, this is a monthly event that I hold with a guest speaker, and we try to explore specific topics and applications of experimental design. And we talk sometimes about things that are new to the whole MOOC, and sometimes we talk about topics that are based on things that are being talked about in the MOOC. We always leave some time at the end of this for some Q&A, and this is a terrific time for you to ask questions. And they could either be about the Coursera courses. They could be questions related to the presentation that our guest is going to give, or they could be questions about a specific situation that you're dealing with, and you'd like to get some ideas from us. If you're on Coursera, you will find these Fireside Chat recordings in Coursera. They're in the Resources tab of your course. A couple of things to sort of remind you about. Please keep your microphones off so that we don't get any extraneous noise during the presentations. And if you do have questions, the best time to do that is to type them in through the chat. You don't have to wait until our guest finishes the presentation to start dealing with questions. Please, if you want to go ahead and enter them anytime during the course, just type them into the chat. Okay, so that's sort of the background. That's how we're going to do things. Dustin, can you advance the slide? Okay, our guest today is Mindy Hotchkiss, who is a technical specialist and subject matter expert in statistics for Aerojet Rocketdyne. She has 24 years of experience in this area between Pratt & Whitney and Aerojet Rocketdyne, which is now L3Harris. She has supported technology development, including hypersonics, additive manufacturing. She has a BS degree in mathematics and statistics and an MBA from the University of Florida, master's in statistics from North Carolina State. She's an ASQ certified reliability engineer, quality engineer, Six Sigma black belt, past chair of the ASQ Stat Division. She represents the ASQ Reliability and Risk Division on the board of directors for the Reliability and Maintainability Symposium. She's on the governing board for the LSR Scholarship Committee. She is an extremely talented person, and I'm really looking forward to the presentation that she's going to give today. So, Mindy, we're going to turn it over to you here, and I want to thank you for taking time out of your really busy schedule to spend an hour with us today.
All right, thank you. All right, I guess I'll just do a quick sound check. Can you hear me?
Yep, sounds good.
Yep, we're all good. All right. Okay. Let me go ahead and share my screen. And we can get going. All right. All right. Are we good?
Yep. Looks good to me.
All right. Okay. So what I'm going to talk about today is experiments in time and space and how that can factors associated with, assuming we can advance the slides here, with these kind of factors can play a role in your experiments. Well, all right.
Well, I'm not advancing.
Might have to click on your slide deck with the mouse.
What's that?
Click on the slide deck with your mouse.
There we go. All right. Sorry. technical difficulties here. All right, what I'm going to be talking about here is just some fundamentals, a little bit about experimentation and a historical perspective, some of the aspects of ways time and space factors can come into play, so the role of constraints, usually we think of them that way, some about measurement, and then some details about some of the physical aspects of the process when you're dealing with time and space, particularly. And so forth. So a little bit about basics. I mean, obviously, I don't have to explain what experimental design is here, but I do want to step back and talk about just the purpose of experimental design relative to the scientific method. So we're testing an experiment, analyzing data. These are fundamental aspects of the scientific method. And DOE really plays a critical role here in trying to establish causality. This is really the only way that you can turn something on and off and understand that you really truly understand what's going on. So, there's a lot of discussion about big data and, oh, if you get enough data, it'll tell you the answer. And that's not true. You have to have the right data. And DOE is really, hugely important in this context. One thing I want to point out before I get started here is that part of the reason I focus on this is analysis methods, the purpose of statistical analysis methods, you're trying to differentiate your signal from the noise. And that's, again, what DOE is trying to do. So to improve the clarity of experimental results, there's two things that you could do theoretically. So one, you would increase the signal, or two, you decrease the noise. We can't, as experimenters, you don't necessarily control the signal, but you can control the noise. So this is something that is really, I think, critical, but also really not discussed about in terms of the practical aspects of implementation of DOE. So I'm going to talk a little bit about uncertainty and experimentation overall. There's several different types of uncertainty. So to start off, the one that you're going to be most familiar with is aleatory uncertainty, and this is natural variation. This is uncertainty due to the inherent expected variability in the part or process. It's associated with natural variation in your underlying properties. So this is stochastic random uncertainty. It's observable, it's well understood. This is what we're trying to quantify in DOE. The other thing that's out there is epistemic uncertainty, and this is lack of knowledge. And this plays a much larger role than people expect. And again, part of the purpose of DOE is to try to clarify your lack of knowledge. But you're trying to understand what you don't currently understand. But there is, you can't quantify what you don't know in as explicit a way as you can aleatory uncertainty. This is not typically observable because it's, not understood. It's not, you don't know what you don't know, kind of. These are the unknown unknowns too. So DOEs are subject to both of these, but you're really only going to get your aleatory uncertainty quantified. So circling back to my original topic here, the time and space related factors are really important, unrecognized contributors to epistemic uncertainty here in experimentation. So I'm going to be focusing a little bit more on the practical aspects of how to do an experiment versus the analysis. But these are some of the things that kind of come into play when you're talking about epistemic uncertainty. I'm not going to get into these in detail. It's just kind of a laundry list of different possibilities, but it can come into play with both your data, the model assumptions that you're making, the process that you're using to collect the data. So good DOE practices can really help understand and reduce both the aleatory and the epistemic uncertainty here. And you can use DOE to structure, your experiment in such a way, to try and remove the epistemic uncertainty from your process, whatever it is that you're trying to learn. So a little bit about, I'm going to step back to a historical perspective. I'm sure it's been mentioned, DOE with blocking, originally developed for use by Ron Fisher to help mitigate the effects of spatial variation, particularly for agriculture. specifically is looking at differentiating the effect of crop yields from other causes. So this goes way back. So, I mean, almost 100 years ago now, 1926, 1936, he was publishing on this stuff. So this is randomized complete block design. So the classic, I'm sure you've seen this one so far. The idea here behind RCBDs, you're trying to apply all treatments in each block to enable equitable comparisons. The purpose of this is to remove known or suspected causes of variability. You're going to do this in like you may or may not actually know what the underlying landscape is, but often, most frequently not. You don't necessarily have this information. You're just trying to remove the blocks or remove the variability from potentially known causes, so you can see what the effect of your actual, the thing that you care about, your actual treatment, what that actually is, without being excessively variable. So to be most effective, a block should be similar, so homogeneous within itself, but each block should be as different as possible from each other. So heterogeneous between the blocks, but homogeneous within the block. Now you're never going to know after the fact how effective these were, because you only get this choice once. And this is where the epistemic uncertainty comes into play. Like, what would be the optimal block in a given situation, right? Once you've made that decision, you can't actually change that. You're not going to be able to go back and rerun your experiment with a different blocking typically. You can. All right. So here I've given a couple, block options. Say you had this surface, there's 3 hypothetical ways you do it. So you got this quadrant option. Whatever, if you could do a vertical stripe, you could do a horizontal stripe. Now, so the effectiveness of how well I do, like which choice of block I make here is not necessarily going to be quantifiable. But if all blocks produce the same outcomes, the factor is not necessarily unimportant. It just may not be optimally blocked. So this is something to take into consideration here. I want you to, so the purpose of this is for us to think about what happens if this is our underlying surface, or the landscape, the spatial landscape. So dry to wet, hot or cold, whatever it might be. So if we look at these cases here, if you look at the vertical stripe, you're not getting anything out of this, because if you manage to block if you arrange all your treatments within each block here, everything is going to see the entire, underlying variability, and that's all going to get translated into your response variability. You're not going to be able to isolate anything there. On the quadrant option, you get kind of a partial benefit. So the top 2, for example, you can see the more green ones, they're going to be more similar, but you'll be able to separate them from the blue ones, which are also going to be more similar. So you get some kind of effect from that. Where you really get the benefit from this particular case is the horizontal stripe option, where, you've got the top case here is all green, the bottom case is all blue, and then you're sort of moving along the gradient. So this is where you're going to get the most realized benefit. If you're looking at your treatment effects, you're sort of pulling out this impact of whatever the gray-blue gradient is, and you're going to be able to see your results a little bit more clearly. So this is kind of what I'm talking about in context here. A sort of simple motivation for, there is great benefit to looking at these things and understanding, and they really can influence your outcomes. So blocking generally, it's going to help mitigate your variation in response due to sources of variability. But the choice of which block do you use in terms of how you set up your arrangement, it can certainly influence your outcomes. All right. The same thing happens in time. You can imagine here, hypothetically, I've got 4 different phases. What if I'm doing an experiment over an extended period of time? There's underlying factors there that you're not necessarily aware of how they behave. I mean, you could have things, moving seasonally or sequentially over time. You could have shifts and drifts and, changes and other processes. So if you consider, a hypothetical experimental test series conducted over an experimental, an extended time period, there's a lot of, in addition to just the logistics and practical considerations associated with this, There's also all these underlying factors with trying to consider, your machines, your materials, your environment, the people, the processes, all these are changing over time. So how do you mitigate the effects of this? So it becomes very important to define baselines and establish controls. Like in medical world, we see a lot about control variables, and it's not something that's very common in engineering. But when you do something where you have data being collected over an extended time period, it really is very beneficial. Like you need some sort of common basis in order to compare back to. So these are just different things you need to take into account. So we talk a little bit more about constraints. These are, to me, these are more than just limitations. These are opportunities. So typically, you get people, okay, I have a deadline, I've got this, I've got a certain amount of budget, I got to have an answer in 3 months, or 2 weeks or whatever it is. How, these are restrictions. And so it might be physical constraints, schedule constraints, computational constraints, with computer time and so forth. So all these steps take time. Anything to do with a DOE is a very physical. Even in engineering, or even a computer experiment, it's still something that takes a lot of time to run, or has the potential to run a lot of time. So understanding the details about the process and the system are really very valuable. You need to understand everything up front. Space and time constraints, they limit experimental scope sometimes, but they can be leveraged. Usually projects can't afford indefinite delays for research. If a question is being asked, it means they need an answer. You often have multiple objectives. There's not, you don't have time to do a research project typically, in practice. It's something needs to be done, it needs to be done soon. You might have data. Just because you have data doesn't mean it is meaningful information. So part of what you're trying to do is convert what data you have into information and knowledge so that you can make a decision about something. There's usually some end purpose to whatever it is that you're doing. And somebody's going to be, trying to make a judgment based off your results. And so that is something that's really critical to keep in mind as you're going through and setting up an experiment. So your focus should be on obtaining sort of actionable, what's the key information that you can get in a timely way because your results are being used for decision-making purposes. And you can leverage your constraints to develop a more efficient and effective experiment. I've seen a lot of very innovative things happen because somebody said, oh, we can't do that. So, okay, how can we get an answer that we need? So let's go about it a different way. And we wind up, finding something that is much more effective, than the original plan. So, all right. One thing we wind up doing, I'm not going to talk a lot of specifics about time thing, but sequential experimentation is something that's also something that people need to learn as they go. Here I've got a sketch of what an adaptive Bayesian experimental design might look like, where you start off with a small matrix, you're adding more sort of sequentially as you go through. These are hypercubes intended to be sketched out there. But you could, one of the, this can be compressed to to the point where you have, after every data point, almost, a decision needs to be made as to what is the next optimal data point that needs to be, what would be the next data point based off your results if you're truly, doing a real-time learn as you go kind of approach. So Bayesian optimal design is one approach here, trying to augment prior matrices. There's other, sometimes when we're doing an experiment, and particularly technology development or R&D, you don't know what you're getting into until you get it started, and sometimes decisions need to be made on the, on the fly. So having a structure, something set up in advance where it's all very well planned out. I would say planning is really critical for laying out all the details of how, how is this experiment going to proceed as you move through time. So, all right, I'm going to talk a little bit about the multidimensional nature of measurement here. There's traditionally sort of scalar world, we're dealing with one-dimensional point. So for every response or every y, you're gonna have a set of x's, or one x for one y. That's not really the way it is in the real world. There's especially when you start talking about spatial and temporal factors. So space here, you might have 2D, so a plane or a surface, if you can imagine that's a surface there. You might have a different response value associated with a two-dimensional layer layout, and that would denote a physical location on a surface. In 3D, again, you might have a response associated with some location in a volume. So it's denoting some physical location in space. And you run into issues here with physical viability too, as you move into, space, like, okay, we can't actually create, create a specimen in this particular location. Things might not be viable. And then you move into time, so 4-dimensional. So here where responses, may be fairly complicated. It might be a function or a profile collected over time. It may or may not have a spatial component. You could be doing a space or a surface or a volume, where those measurements are being collected over time. The time of measurement itself may affect your results. There might be induced biases. Anyway, there's numerous scenarios for different combinations of inputs and output variables here in the 4D world. But basically, all these things contribute to variability and uncertainty in the test results. And this affects experimental repeatability, which is something if you read the literature, there's a lot of concerns and issues out there associated with people being unable to repeat their experiments once they've been, published, and they go out and other people are trying to, it's supposed to be the gold standard, right? You're able to repeat your experiment. And things are not as repeatable as they had expected, and so that's drawing into question a lot of results, published results and so forth that get out there. So I'm going to talk a little bit more about one thing that I've encountered that may be contributing to that, particularly when talking about these more complicated results that people might be trying to look at. So for example, this is just kind of a notional sketch here. Say you had this kind of profile, and I do want to say, like, these kinds of things are definitely out there, and usually they have a physical aspect to them, like something is being turned on or turned off, or it's a reaction. There's a physical component to that. This is behind the scenes. It's not just randomly deciding to follow this pattern. It's being induced through some intervention. So all of these, transitions, for example, might have physical, meanings and interpretations to the engineers who are used to looking, who want to look at this particular data for whatever reason. So I want to talk about how people might look at these, traditionally, historically, like you could go through and do a data summarization approach. So for example, calculate the mean, calculate the standard deviation, min, max, range, very basic summary statistics. If you're looking at the, if you don't really, and this is why subject matter expertise is also important, because just clearly looking at this graph, that's probably not going to be the best representation of what your data are there, but it depends on what the question is that's being asked. Another way to look at this that might have particular meaning to engineers would be, okay, let's look at what exactly are these physical things that happen. So we start off with some initiation level. At some point, it drops down. And then there's a time, how long does it take to drop? How far does that drop take? What's the height of the next plateau? How long does it take to get down to some whatever level here? Someone, you could measure all those little pieces if you wanted to. So what I'm trying to get at with this is just point out that more complicated data are often summarized or reduced. And if you don't really understand what they're trying to get at, this is also going to add variability to your inputs and outputs, when things don't go as expected. So for example, say I wound up, if things happen here, so say if you look at this yellow curve and I don't have a peak, how am I going to summarize it? What if I have two peaks? These can cause outliers in your data if people aren't, you need to backtrack and look at exactly what's being measured and how they're understanding. Because oftentimes the question of measurement is really like from a statistical background, we tend to take the numbers on faith that whatever measurement was made is a gold, is golden. It is what it is. That is not necessarily the case. And one aspect of this might have to do with this data pre-processing that comes into play, which can add variability to both your inputs and your outputs. So this can happen on both ends. Are you really controlling your system to the point at which you think you're controlling it, or is there something, what exactly is happening in your response variability? So these methods here may not be robust to generalization, and they may result in the loss of information. So one thing that can happen here, the more advanced methods would be the analysis of profiles. I would take into account function morphology, the actual shape of things going on here, but we're not going to get into that. But this is just sort of traditionally approaches of these are things that can cause issues. So, and this could work this could materially impact your conclusions at the end of your result, just because you're working with different data. It's not repeatable in quite the same way as intended. So another concern was spatial considerations. Of course, the question, how many parts do I need? So it's not a simple question. It's an even less of a simple question than it is just a typical sampling. How many do I need? So there's a lot of other factors that need to be traded here. So if you're looking at trying to figure out how many specimens can I put in a surface, for example, what's the design of the specimen? Do you have control over it? What are the options? How big does it need to be? What shape is it? Can I stack them? I mean, what arrangement is available? What layout can I do? How much space is available? How much area is consumed by each one? Do I need to separate them? So sort of what's the density or intensity of the distribution that I can put on a surface or in a furnace or wherever I'm trying to arrange these things. There could be questions of orientation. So like, all right, vertical this way, or clocking. There's like multiple ways you can think of orientation. What limitations do you have? What other concerns, other supplemental information. And then like, okay, let's talk about your conditions, your treatments. How many factors are you dealing with, the variables? Are you trying to do something with hierarchical hierarchical or the nesting kind of factors? What's being measured? If you're measuring something on a binary pass-fail basis, then you're going to need way more specimens than you do if you are able to quantify. So trying to quantify is always beneficial. What type of outcome? How long does it take to evaluate? I mean, if you're going to make a whole bunch of specimens and then each one takes a month to measure, that's not very viable either. So that's another way in which constraints and limitations come into play. So a little bit more considerations for specimen design, the physical nature of the specimens, the shape, the dimensions, aspect ratio, orientation, clocking, like I mentioned, key features, subfeatures, what would make it better? How is it more informative of the questions being asked? How long does it take to create, evaluate? Can you simplify it? Iterate it, how to maintain traceability. Basically, how can you maximize the information gained from this specimen? Okay, I got a couple little examples here. So say you need to develop a sampling plan under some constraints. So I have a certain number of candidate points in gray. Each location can be sampled only once, and your objectives include minimize the sampling required, characterize the distribution of a lot of surface of different quantities across the surface. There's some standard letter optimality designs that can come out here. I did this in SAS Optics. And there's 4 default options that they provide. So DAS and U. So I'm going to show you what the different things provide. So D here was the default for optics. And if I look at the results here, I'm trying to get 7 points. And this is not, it took a lot to actually get 7 points. Most of them, it's giving me 6, including a replicate, which I can't do because that's not viable. I'm not allowed to replicate, or it's destructive sampling. So these aren't viable. A gives me a similar kind of thing, but slightly more symmetric. This one only gave me 5 with 2 replicates. So these are just I'm trying to emphasize the importance of actually looking at what you're being provided as an optimal result, because it may not always be optimal in terms of what it is that you want to look at. So S here provides a little bit more symmetry and stasis. It and U are both rotatable. In this particular case, we went U here would be the more preferred option because it provides a less redundant information, and that it's giving us more points at different distances from the center. So here I have all 6 points are being pushed to the extreme, and the one in the center. Here I have 3 at the extreme, and then 3 at an intermediate level condition, and 1 in the center. So that gave us, gives you a little bit more ability to actually look at what your variation is at different distances from the center. So it comes in, you need to think about what exactly is the context of your question, and what's important to the engineers or whoever you're working with in your particular environment. But the main point here is that statistical optimality measures are not going to be providing equivalent spatial coverage quality. U here in this case is particularly does have space filling criteria that it's trying to work to, but it's different from standard methods there. Okay, here's another example. So consider a set of 4 factors at 3 levels each. So simple factorial, 3 to the 4th gives you 81 runs. Okay, we can't run 81 runs. All right, mix of qualitative and quantitative factors. So how can you arrange this? Just simple combinatorics. If I take 81 combinations, all right, do a 1/3 fraction would be 36. I've got some flexibility here in terms of how I want to define things. Like I can decide how many layers I want up and down. I want to decide how many I want to put on a given, how many builds I want to do, or how many runs I want to occupy here. So, this is something like these details are things that need to be worked out with the engineering team as you're trying to figure out how exactly are we formulating this problem from a technical engineering standpoint to answer the questions of interest. So in this particular case, so here, again, this is kind of a notional example, but you can use like level 0 as a control, and we have 9 levels, so we have 10 levels altogether. And it was double blocked by run and level. And if you do that, so you can have each factor level represented 3 times for each run, and each factor level represented 3 times for each stack level. So you can simultaneously block by multiple factors to achieve a little bit more balance, as opposed to just randomly assigning your factors or your treatment combinations to different levels or builds. So that this contribution from the spatial noise factors can be isolated from treatment effects that you're trying to actually study. So that's another example. Moving back to the spatial time, I talked a little bit about controls already, so I won't dwell on that. One thing you just need to keep in mind is that experimentation over the extended time is going to require more replications. for rebaselining and to check for process shifts and so forth. So that also is going to impact your quantities and, just your verifiability of your data. So, so I talk generally about, just wrapping up here, just the impact of signals on noise. So if you start off here, if you can imagine your nominal level here, and you're trying to distinguish a signal that's up at this level, if your variability, your uncertainty is really wide, you're going to wind up with a non-significant result. It might be suggestive, but not conclusive by any means. But the more that you can reduce that uncertainty through whatever factors, through control and understanding, exactly what's going on in your process, and trying to keep mitigating the effects of potential things that could be influencing this, what could be contributing to noise. The more you can reduce that, the more your signal becomes more clear. It's much easier. It's much easier to, I much prefer to have results that are like hit you over the head versus, when you're doing an analysis. I don't, if I can make a simple plot and say, hey guys, this is what's going on, it makes my job a whole lot easier for in trying to, communicate results and so forth. So anything that I can do personally to, reduce the uncertainty associated with a particular problem is really beneficial. So explicitly considering and controlling like spatial and time factors is going to help you generally. I did have a few just general comments. So these are important factors that may be ignored or underestimated. A lot of times people think that they're, that they don't have as wide an influence as they do, but they really can be a significant source of variability. Blocking can help. It's sort of a classic solution, but very effective. Arrangement in space, 2D and 3D, can be utilized to allow for improved balance and mitigate the effect of differences. Be careful with statistical efficiency measures or optimality measures. Understand your measurement processes in depth for both inputs and outputs. Insufficiently robust, I guess I would call them, data pre-processing practices. If your data are being summarized or reduced, can induce variability in the data, including outliers. Not all sources of variability will or can be quantified. In technology development, processes are not necessarily well defined. Often it's technology, it's development, so they're learning as you go. They don't understand the physics. They are learning the physics. They're trying to understand the physics, and part of that is, that's your contribution, is to help them sort of work through all this, and it may involve a lot of iterations. So experimenters should have an awareness of potential complications, work to mitigate potential issues through controlling or monitoring related input variables. So there's more to ask when involved in a DOE than how many factors and levels. It's really important to get into the weeds. Leverage interdisciplinary resources. Usually you're on a team, you have a lot of subject matter experts available, like they all know a whole lot, way more about whatever's going on than you do. It's very, you can't possibly understand all the nuances of what it is that's going on. So just trying to talk intelligently about it, it's very helpful to understand the basics. But there, in my experience, everybody's, more than happy to, discuss their experiment, the background of the process, and what it is that's important. Constraints can be helpful. It adds rigor. It doesn't let things drag on forever. It's important to get things done. And just be aware that experiments are very physical in nature. So both with respect to the time and the space related logistics and the practicality. So if you're making a bunch of parts, where are they going to go? Who's going to carry them? Are they heavy? Things like this, how long do they take to process? Is it in an inspection, somebody looking at a part, it may take more time than you think it should. And all of these things need to be sort of factored into the schedule and the experiment, and understanding, trying to interpret the results when you get to the end of it. So, so I had just good luck in your future endeavors there. So, questions?
Mindy, thank you very much. This has really been an interesting talk, and there's a couple of things that you pointed out that I'd like to talk with you about. There toward the end, you were talking about some of the practical, logistical aspects of things, and one of the things that just popped in my mind is maintaining physical control of the experimental units. Can be really important, and I have a hilarious example of this that I'll share with you. Some people I know in a company that will remain nameless. Okay, we're trying to figure out how to make some electronic parts that go in the engine controller of an automobile. And they were having lots of difficulty making this, the semiconductor, having a lot of difficulty making this. And so they ran a series of experiments over about a 2-week period. I mean, they literally shut down the routine operations in this fab so that they could run this experiment. And toward the end of the second week, they had all of the experimental units. They had everything done. Okay, all they had to do was to get them into the lab and do all the measurements on all these units. And so a friend of mine was the fab manager at the time, and so I knew what was going on. And the lab people said, if you will leave these parts right here, we will take care of doing this over the weekend. And when you come in on Monday, we will have all of the data and we'll know exactly what to do to be able to make these parts so that our customer who is dying for these parts will be happy. So he comes in on Monday at like 6 o'clock in the morning, just to be really, on top of things. And there's no report from the lab. And so he starts checking around, and he runs into some of the operations people. And he says, have you guys seen my parts? And they say, oh, you mean the parts that were in this area over here? He said, yeah, those are the parts. He says, well, we saw them, and we did a quick QA check on the parts, and they all looked like they were within spec. So we shipped them to the customer. He said, yeah, he says, these parts were on an airplane on Saturday morning, headed to Korea, which is the assembly site. And they're probably already on the printed circuit boards that we're going to send to the customer. So didn't maintain physical control of the experimental units, right? That's the worst example of that I've ever seen. Okay.
Yes, definitely. Another thing to take into account too is the traceability. So where I thought you were going with that was like, oh, they all got mixed up because they weren't labeled, which is
that I've seen that too.
Yes, I figured.
I've seen that too.
Yes,
and you had one other figure that I was really interested in, and that was the figure where you were showing the output was this curve that was going out and then down and then up again. I tend to think of those kinds of responses as profiles. Mm-hmm. And you do run into experiments fairly often where the response is a profile.
And, yes,
and
it's very common.
Figuring out how to deal with that is sometimes quite complicated.
Yes, yeah, it's not readily accessible. Like you're talking about, there's a functional data analysis and so forth with the handling the shapes and the profiles. Yes, so yeah, that's the more advanced state-of-the-art kind of methods. But a lot of historical things certainly are, and that's not also generally available to the public. I mean, it is starting to be more commercially available, but is not sort of generally well known or recognized. Even in the statistics community, there's very few people, I think, who have exposure to that or can analyze it intelligently. So it's or there's a lot of but yes, that's certainly something. I mean, I've been seeing those. I mean, my entire career is everything's got a profile, and okay, how do you handle it?
Yeah.
And so it's yeah.
Well, I had a PhD student a few years ago that worked for a company that manufactures airbags, and through working some with him, I got some idea about how to deal with profiles. A lot of the experiments that they ran in their business, the response was a profile. You know, how long does it take the bag to inflate, and then what pressure does it achieve at the end? And you know, they have to control both of them. They have to be able to design the darn thing so that both of those features are optimized in some sense. You can't have the thing inflate too fast because it will break your nose.
Mhm.
And the same thing with the pressure. You know, if it's over pressure, you could be seriously injured by the airbag. So
Mhm.
you know, kind of looking at how they ran some of their experiments and analyzed the data gave me a bit of insight about how to deal with that. Interestingly enough, there's a lot of literature on that in the SPC world. There has been a lot of work done on monitoring processes where the output is a profile. And a colleague that you and I both know very well, Bill Woodall,
Oh yeah.
he is really an expert on profile monitoring.
Mhm.
He probably knows, he's probably forgotten more about it than anybody I know. He's really very good at it. He and I had an NSF research project for a couple of years where we worked on this and had a couple of PhD students work on the problem. And Bill went on and did much more work in the area. And so, you know, one of the things I would suggest to people running experiments that have profiles is take a look at the SPC literature and see some of the techniques that have been used there to capture the information in profiles. It could be very helpful. Could be very helpful.
Yeah.
So
Yeah, definitely.
you know, I really enjoyed those aspects of your talk a lot, because I've run into some of that myself over the years. That blocking over time is so important.
Mm.
It really is, because things drift, you know, and
Oh yes.
and if you're running an experiment that takes several days to complete, finding some way to block on time is
Mhm.
really critical.
Yeah. Another thing that can help in that case is making sure everything is recalibrated, because calibration drift and so forth. And so
Yeah.
one thing I have seen is, okay, before we do our experiment, or we're just always going to make it a ground rule that we're going to calibrate again right before the, make sure everything's at least consistent condition, before you proceed with doing the next set of test runs. So, and that's something I think, again, it has to do with measurement and, gauge standards and so forth. And I think the statistics community in general, I think, doesn't pay too much attention to calibration typically.
But you should.
Yes,
I know.
I think so. It's important.
The students
Yeah.
that take my experimental design course here, they have to submit a project proposal. And one of the things that I always insist on is explain to me how you are going to measure the response. Okay. And then
Mhm.
explain to me, how are you going to ensure that this response measurement remains consistent over the course of the experiment? And you know,
Yes.
a lot of these kids now, they're graduate students in engineering, and they've never thought about that. You know, they've
Totally.
it's never entered into their education anywhere. And
Right.
I feel like
Measure.
I'm the Lone Ranger trying to explain how important this is to them, because measurement systems deteriorate.
Yes.
Yeah.
I mean, that's the entire purpose of there's standards, and we don't think about it because we're so used to everything being, the stuff that we deal with on a day-to-day basis, but engineering equipment and so on, there's a lot of especially the more narrow a tolerance that you're trying to deal with. It's one thing if I'm trying to, deal with something that's large and, okay, how do I handle it? But the more you go towards an extreme, then the measurement system becomes more difficult or it could potentially be causing more problems. So as you go to an extreme or the finer the resolution you need, right? If you got something that's really tight, you need to be able to measure it really tight. And those are, it may not be sustained, that level of resolution may not be sustained over time.
Right. And sort of another kind of, measurement type of thing is in many experiments, you have subjective responses.
Mm-hmm.
My students always want to do some really interesting experiment. They're going to make chocolate brownies. Okay. And they're going to investigate things like different brands of brownie mix and different ingredients and cooking methods and all this stuff, which is just great. But then what they want to do is they want to have a response measurement that's entirely subjective.
Mm-hmm.
And so what are they going to do? Well, they're going to take these 16 different recipes that they've produced, and they're going to take a sample of each one of them, and they're going to rate it on a scale from 1 to 10. Just useless.
Uh-huh.
I mean, I have seen so much of that kind of data over the years that what you end up with is a whole bunch of clusters of 7s and 8s and a whole bunch of clusters of 4s and 5s, and you get very little discrimination. That's very useful. And so I always try to tell them to think about another way to do this. How about taking your subjective responses and doing forced ranks? Take the best one is number 1, the next best one is number 2, and all the way on down to the last one is number 16. And now you've got discrimination. And of course, it may be darn tough to do the ranking, but that's
yes. You might have something coming up there. You'd be able to at least do better versus worst. And
sure. And if you have a panel of people doing the ranking, and you work with the average ranks, that washes out a lot of the uncertainty that's associated with telling the difference between the next best one and the next best one. So.
Yeah. I think the important thing to do in whatever context is to add some structure to it. I mean, whether it's standard work or, common, work practice guidelines or whatever. And back when I was in grad school, I worked at the EPA, the Emission Measurement Center. And one of the things that they did there, they were out there evaluating like smog, the thickness of, different things. But in order to measure this, everybody had what they called calibrated eyeballs. They all went through training to, yes, like, okay, can you differentiate between whichever, level of, the degree of opacity or the color of the opacity, so that they were all on the same page in terms of, what it was that they were actually evaluating. So
I had a similar experience when I was at Georgia Tech. I did a lot of consulting work for Coca-Cola, and I worked quite a bit with some of their flavor chemist people. And one of the projects I worked on was developing the artificial sweeteners that became part of what today is Diet Coke. Okay, and the Coca-Cola company does a lot of taste testing, and they had a group of about 50 people in the company that had gone through exactly the same kind of experience that you're talking. They were trained taste testers. Okay, and whenever you had one of these crazy, sweetener experiments going on, you could reach out and get a panel of 10 or 15 people to be involved as your taste testers. And, and you can train people to be pretty good at this.
Yeah. Between that, or at least write out, all right, here we have structured instructions and so on that's tailored to your experiment. And
right.
so on, like, what is it that you're supposed to do? make sure they're at least all doing the same thing.
Right. Everybody's looking at things with the same scale.
Using the scale in the same way. And that's one thing with measurement systems. I've done a lot of measurement systems analysis over the years, and that's another aspect where it's like, oh, especially when you're dealing with tight tolerances, it can be very surprisingly a variable.
Right.
So, okay, what can you do to improve it, and so on. So,
well, we have a couple of questions that have come in, and maybe we ought to take a look at those. Here's the first one, and I'm going to read the question. I don't know whether you're able to see it or not, but let me read it. It says, I have a question regarding robust process design. And it says, I understand that noise variables are variables in which you have no control over the input and vary randomly throughout the process. But I noticed that the experimental arrangements require that these variables be set at a specific level. How do I set a variable I have no control over? And he says, I feel like there's a hole in my understanding in this regard. Can you clarify? Well, let me take a shot at this because I've been involved in some of these kinds of experiments. And basically, when you have this kind of situation, you have to figure out how to run this experiment in an environment or in such a way where you do have some control over the noise variable. For example, you may be able to run the experiment in a laboratory setting or a pilot plant setting where you can control things like environmental temperature or humidity or factors like that, which vary routinely during the normal operation. You may be able to control, for purposes of your experiment, raw material properties that vary uncontrollably in the material that you routinely receive. But by sorting raw material and classifying it, you may be able to control some of those factors for purposes of a test. And that often requires a lot of thinking as to figure out how to do that. It's often not easy to do. Now, if you really can't do any kind of control, hopefully you can at least measure what these noise factors are, and then you can treat those as covariates in the analysis. And I've had to do that a few times too. I can remember one experiment where we were looking at a physical property of a chemical product that depended on the incoming raw material viscosity, and there was no control over that viscosity at all because it was coming from the plant next door. Okay, that they were refining something and we were getting what was left over, but we could at least measure that viscosity. And so we were able to treat that as a covariate in the analysis. And so in effect, we were able to do essentially the robust design modeling and analysis, but treating the variable as a covariate. And so that would be my thoughts about answering this question. But it is tricky sometimes to try to figure out how to control an uncontrollable variable for purposes of a test. Do you have any thoughts?
Those would have been exactly my same two suggestions. It would be, if you dig into it enough, you can probably figure out, like, if you're doing the experiment, you're probably going to have some of the work in the lab. You can probably control it. The other thing that came to mind, in addition to the covariates, right? If you can't, you just measure. But there's also the accelerated testing route, which, all right, you're going to create conditions that are more extreme in order to degrade the product sooner. So that's a little bit more complicated, and you have to understand the physics of the relationship so you can backtrack. But that would be the other avenue, perhaps. That's a very good suggestion. And in fact, we just recently had a fireside chat where my guest was Caleb King from Jump. And he talked about accelerated life testing. So there's a prior fireside chat that you could go and take a look at and get some insight on that, because that is a topic that we don't really talk about in the MOOC, and which is why I asked him to come and do that. So that's okay. Hopefully we've given this person some food for thought here. Okay, and
have we got another one, guys? Oh yeah, oh yeah. If I have a sequential process with 6 operations mixing 3 elements, okay, where parameters such as temperature, time, and pressure are controlled, which design is advisable to apply? Is it possible to apply a stepwise experimental design? I'm going to assume that what they're talking about here is sequential experimentation, where you work with each operation at a time, as opposed to running one big experiment where you vary factors across all of these operations in one big experiment. I have seen that done. One example that comes to mind is I've seen experiments in semiconductor manufacturing where you've got 2 stages. You've got one stage that puts something down on a wafer, like chemical vapor deposition or sputtering or something like that. And then the next stage is you're etching some of that stuff off. And so they'll run an experiment across both of those processes at the same time. And there'll be varying factors in each of the processes during the experiment. I've never seen it done with as many as 6. I think that gets kind of complicated. And
Yeah.
I think I would be focusing more on working with each process step individually to try to understand what it's doing. Thoughts on that?
Yeah, again, probably about the same. I mean, I do like breaking up more complicated processes into smaller processes. So the more that you can like differentiate, take your 6 sequential steps and say, okay, I'm going to only look at the first few first, and let's sort of figure that out. But it kind of depends also on how things are being evaluated. Like, do you have to go all the way to the end, or is there some intermediate kind of measure that you can look at sort of halfway through and say, okay, how do I know, when we optimize things at this point, can you break it up? But yeah, I mean, if you've got to go through and do the whole thing, then you got to go through and do everything all together. But then you wind up, if you can do a large experiment, but then you got a large experiment to deal with.
Yeah, and the logistical complications of that are
yeah,
going to get ugly.
Yeah, I'm a big fan of making things simple.
Me too.
So and just work on it piecewise, break it up.
Yeah.
As much, in ways that make sense.
Yes, and if you understand the pieces, eventually you'll figure out the whole thing.
Yes. And there could be interactions between those different,
oh yes,
the sequential steps as well. So, you got to be a little careful about that. But, yeah.
Well, we're getting to the end. We're running out of time. Thank you so much for this talk. This was really an entertaining talk, and there was a lot of extremely useful information there. So, Mindy, I really appreciate your taking time to do this. I know you did a lot of work to put this talk together, and I really appreciate it. This is the end of our session for today. Next Fireside Chat will be in January 2024. We don't have the date pinned down quite yet, but the information about that will be forthcoming. And thank you all for joining. And once again, Mindy, thank you for everything you did to make this a great experience.
All right. Thank you. Thank you for inviting me. It's been a pleasure. So nice to see you.
Good to see you too. Bye-bye.
Yeah. Bye.